Good afternoon. Today I'd like to show you Artwork's latest advances in creating 3D step models from printed circuit board layouts. These step models are now optimized to work with simulation systems that use finite element analysis. So we're going to start with a printed circuit board that has 14 layers. The inner layers use conventional technology for the vias, and then the top and bottom layers use these small micro vias. Alright, we start by importing our ODB file into NetXG. In the output area, we still select 3DI. We won't have any more 3DI for step in the near future. I make sure we've selected Create Dielectric Bodies. To keep everything small, I'm going to select a very small window to do my analysis on. And I'll use Get Data Window here to do that. I'll select an area, say, from here to there. So that's going to be the window I'm going to extract with NetXG. Now we'll execute the program, give it a chance to run. Okay, it finished. Let's look at the output. So there's the little area we cut out of our board, and I'm going to turn off the components. I'm going to turn off these dielectrics so you can see what the insides look like. We can see that there's a number of metal layers, and then there's these large vias that go from layer 2 to layer 13, and then on the bottom side you can see the micro vias. Let's see what the current issues are when we produce steps. Are not really that good for finite element analysis. I'm going to make these things transparent so you can see where there's some interference. You can see there's a pad that's part of the pad stack definition, and it interferes with this metal which comes from another section of the ODB file. You cannot have that if you're going to mesh this for a simulation. Now, it usually causes the mesher to crash. You have to remove that. The other thing you can see is that the via itself is not one nice object. It's actually made of segments between each layer. There's a piece of metal in between there. What happens is that the mesher has to generate many more faces to support many more mating faces than it would otherwise need to if that was a single piece. Our 3DI to step, when you use the FEA option, is able to analyze that and replace that unsuitable via with a one that's optimized for meshing. So how does that work? Well, you go to File, Export, and now you'll see there's two step options, and then the step for FEA is much more rigorous. We're going to use that option. Here are some optimizations and functions specifically for FEA. We're going to remove these duplicate pin objects which interfere with conductors, and that would be all of these guys on all the layers where they exist. We're going to also generate what we call negative dielectric on the conductor layers. And then in terms of the vias, it says merge via parts with the same ID. The program will recognize that and replace that with a single structure. Finally, we're going to replace our circular vias with polygons with 6 sides. We're doing that because we've been told that our FEA clients don't need a lot of faces on their via to get an accurate model. Finally, we're going to make sure that we drill through the conductor and the dielectrics and even the negative dielectrics so there's no solid body interference. So once we've got all that set up, we just click Export. Now we can just export our step file. It goes fairly fast. I'll import it into SolidWorks, and then we can analyze what it actually looks like. So I'm going to import my step data. There's our model in SolidWorks. Let's turn off the components that we don't need, and let's turn off the dielectrics and see what we have. You can see I only have 2 parts that contain vias. One contains the via that runs from M2 to M13, and it's clear to see that it's only a single structure, so that will mesh very efficiently. The other contains the vias that go from M13 to M14. Those are nice single structures. Now let's look at our negative dielectric. So here's our metal 2 layer. Here's the dielectric that metal 2 sits on. When you build a printed circuit board, you squeeze it together, and the dielectric is going to flow into the areas between the conductors. In order to generate that, we take the dielectric boundary, we subtract away the boundaries of metal. What we're left with is everything that lies between the metal. Let's turn on the negative dielectric layer that we've created. You can see that it just poured in between the areas of copper. You have a completely flat surface. If you wanted to apply a boundary condition such as a block of material with a certain temperature, you now have a nice flat surface. I just want to show one more thing, that we drilled through the negative dielectric, the metal, and the dielectrics so the vias reach all the way to the top of the pad. And these faces mate perfectly with the via body. So these are the steps that we've taken to make this step data compatible with any kind of finite element analysis tool.